Okay, it's September 14th, 24 or 16th. My clock was looking weird. Um, we're entering chapter 9 for cohort 6. Um, do either of you want to type or ask any topics you want to cover or explore for 9? Otherwise, we can look through the chapter
I
or
was actually about to, oh, I'm sorry.
go ahead. Good.
I was actually going to ask if we could just like run through the chapter because this was the first chapter that I was like, oh man, we are jumping into creating this model. Could we just run through one time into going through like what was the data and what was the model that we were actually applying, as well as just going through the loop of figure. Oh, I'm sorry, I've lost the figure. It doesn't really matter for that last part.
Yeah, got it. Okay. Pulling back, I think going over the chapter is the first thing that we'll do. Then there's the questions and some notes. And then there's also looking at software. Just speaking generally, maybe we can do that in 1 or 2 weeks from now. Looking at the JAX branch on PyMDP, looking at RxInfer, and looking at other empirical work. Let's start with the chapter though. Okay. Second half of the book, applying active inference. Coming fresh off of chapter 6 recipe, chapter 7 and 8 giving the continuous and discrete time, now getting to using the models that are created for data analysis. That's kind of revealing that in all the previous chapters, 2, 3, 4, not 5, but then 7 and 8, when talking about building a generative model, it's to produce synthetic data, like to run a simulation forward. Here now, we're also, or alternatively, looking at a setting of having a certain structure of data and then seeking to recover latent parameters instead of specifying the latent parameters and then generating the synthetic observation-like data. Um, our general goal is to recover the parameters of the generative model that system of interest uses to produce behavior, subjective model. 9.2, meta-Bayesian methods. This is really well summarized in figure 9.1. It's like zooming out a layer from figure 4.3, figure 7.3 type POMDP, hashtag model stream 14.1, POMDP that we've been specifying and talking about, minimizing the variational free energy and so on. Zooming out, saying, okay, not just the mouse in the T maze, now considering the observations for the mouse are actions for the researcher. And then conversely, the output behaviors of the mouse are objective observations for the ethologist. Interesting how it's using the notation of like the subject centered view because it's calling them whereas you might also call them actions of the researcher, and then it's like it gives the hint of the suggestion. Okay, yeah, you could make a policy if you wanted to do policy control variable, like another pi sub scientist, and then have that connect to O. But otherwise, we're just taking this as a given. So we're just taking that as the input data for here. And so that subjective model, which does the forward inference, which is like the kind of perception action loop that it's focused on, that's happening with a given set of observations in an experimental context and outputting some behavior. So it's kind of showing, okay, the data, like the input data, here's the information that we knew on where we put the food in the T maze, and here's the actual sequence of moves that the mouse made. Brief little statistical interlude that starts to bridge back from this question of reducing uncertainty of the unknown parameters of interest, figuring out the subject's prior beliefs. It's like we know where their eye saccades were. That's just empirical. Or we know which things they bought. That's just empirical. But then to do belief modeling, cognitive modeling beyond just the pure behaviorist layer, then that is reducing uncertainty about these causal parameters of interest. So how are those going to be analyzed from real finite data? They go into variational Laplace. This is something brought up in other textbooks, in the SPM textbook. Okay, 9.3, 9.4, giving like two different ways, more of a classical statistically parametric, and then more of a empirical Bayesian approach to fitting a first kind of structural layer on these hidden belief distributions. Variational Laplace centers a Gaussian in the log likelihood. Thomas Parr discusses this in 57.1 or 0.2, fits a Gaussian on the log likelihood. So in the actual likelihood space, it doesn't have like a or it's a parabola in the log space, and then like it looks different in the non-log space. But this just fits a central tendency on a belief distribution parametrically. That doesn't require any that fits a simple distribution to data. Parametric empirical Bayes takes a slightly different approach, which is like to kickstart the estimation of the prior from the empirical overall distribution of the data, or like a previous or a related experiment. Here's the instructions for doing the model-based analysis. So collect data first, or maybe the data are already collected, like it's a meta-analysis. So just like the previous figure, the data that are important here are like, the input, which arm was the food on, which color was the strobe light, and then the context of the experiment. If only to normalize out and say, yeah, actually the digit in the minutes column has no correlation with this, but it might be something just included. Formulate a POMDP model. So that's, as we saw here, with taking the subject's kind of first person perspective on taking in observations and how it does its belief construction. Here's a map describing its belief construction representation, and then how that information becomes actionable. And then we have just empirically the information on the temperature of the room and the T-maze. This information in the list is summarized in figure 9.2. So we had data collection, or we're reviewing some data that were already collected about the T-maze. But we have the lab type data. Then we have chapter 7.3 POMDP for the T-maze. 3, specify likelihood function, equation 9.2. Actions selected depend on the observations made. We could look more about this, but it kind of gets to the punchline of the, and it's kind of subtle with the bold and the bold being vector. But the policy that's selected is the argument that's minimizing the variational free energy over all of the policies. So that's like how decision making is going to be evaluated from the outside, as if it's minimizing free energy, as opposed to other approaches, like as opposed to it maximizing reward. This tells us how the model should be used to calculate a likelihood. This typically calls a POMDP solver SPM MDP VBX. It's interesting. These are like super oft referenced scripts. They're in MATLAB. There are MATLAB engines that can call MATLAB if you have a real license from other languages. So it can be really called within Python. Um, Other options, there's Octave, which is like an open source cousin of MATLAB. Oh, well, there's SPM standalone, which is actually MATLAB, but it's just like a reduced kind of single SPM only download. Then there's Octave and Patches. I don't know how well the coverage is for patching certain things of SPM MATLAB into Octave. There's Julia SPM, which is an attempt to port over to Julia. There's PyCall and Julia call. So basically calling languages within each other. And getting these scripts, which are kind of key central pillars of a lot of the inference across prior papers, getting these scripts into non-proprietary, more easily callable methods and implementations, it's huge. 4, specify prior beliefs about the parameters, terms of expectations and precisions. Here, setting a prior just to give an initial condition. Again, that could be parametrically gleaned from data, or it could be empirically set like PEB. Inverting a model is using this rearrangement that's possible with Bayes equation and using kind of algebra and separation from there to calculate what we're interested in, which is like the belief, the distributions of subjective beliefs of the mouse in the T maze, conditioned upon all the stuff that we're putting into the model. Whereas the synthetic generative direction would be given the ad hoc specification of belief distributions. Like, what if it thought it was 3 times more likely? Then you could generate realistic trains of behavior. You take those final behavioral data estimates, and it's like, here's 5 days of the week. We did the experiment, and belief whether we calibrated or didn't calibrate, like whether it's just a fear score or it's calibrated or it's somehow normalized, like it's a percentile or something like that. And then this is like a figure, just normal figure from a paper. We had 5 different condition groups, and their belief on this distribution here, it was 7 plus or minus 1, 5 plus or minus 1, 1 plus or minus 1, -1 plus or minus 1. And then you can just do a t-test. And then you put little stars, statistically different groups. That's the main outline for 9. I think it'll be awesome to see fully worked cases. Like if we can get a repo that has all of these steps labeled this way. The last piece is 9.6 gives a few examples. 9.3 looks at isochade in a continuous and in a discrete control setting. We could look to the paper if we want to look at that one. Table 9.1 reviews many citations where these kinds of methods have been applied. That's the chapter. So it's interesting because 9 is like, it's kind of like a Jimi Hendrix thing, if 6 were 9. And then 6 is like the recipe for building the generative model. And then 9 starting, well, we still have to build it as per 6. But it's another recipe. But they don't call it a recipe here. Any thought, or what should we continue with?
Whenever they introduced, I think it was the variational Laplace, I may be misremembering. They casually brought up, oh, yeah, you don't really need to understand this, but this is predictive coding. This is just the example we're using. If you don't mind, could you say a little bit about, if I'm remembering correctly, predictive coding, as well as in your experience, like what kind of models are being used right now in active inference in general? Is it all going to be like just taking about the same model and trying it through different things? Are many different models used whenever you're actually building these experiments, or is it just really, really diverse?
Yeah, good questions. Okay. And then let's look at this page. Okay, 2007 here. 2007. All right, first let's see where it came up in this. Okay. This is totally pending. Just seeing one just kind of one take on it. Look, Octopus or others might be able to bring a lot more detail in. This is coming from the parametric statistic approach. So kind of classical pre-computational, if that at least pre 1900s, let's say, approaches to fitting distributions. Um, Whereas once you can do parametric empirical Bayes or like sampling based methods, then there's this whole alternative branch of doing sampling to fit analytically intractable distributions. But if it's going to be like, well, how do you make it more analytically tractable? That might be advantageous or simple, might be ineffective, but also it really does have certain advantages. If it totally mangles the underlying structure, then again, it wasn't adequate. So this isn't to say that it's adequate for every distribution, but if you do a sampling based approach, then you have to also put a nice behaving continuous distribution over that, or choose to not do that because the sampling gives you a good shadow or kind of scatter if you do it well, but it still doesn't have the kind of smoothness. So it's kind of like if you want to get to the parametric, why not go directly from um the data instead, whereas now it's sometimes sampling is thought of as an alternative approach, but it doesn't really get to the same endpoint. This is a incrementally like matrix gradient based method to fit based upon the gradients of a Gaussian or a parabola or something downward facing over log likelihood. And Thomas Parr mentioned it more on the stream. Possibly because it's working. Again, it's whether okay, maybe it is a Gaussian fitting a Gaussian, but then the Gaussian is locally approximated with a quadratic. So then that keeps the approximation of the gradient um possible. This paper describes it. Let's see if there's anything right here. Okay. That's just the preview, but it seems like a lot for the preview. Okay, so maybe for us to learn more about, but it's a tractable way to use gradient information, geometric gradients to incrementally optimize statistical models being proposed, existing kind of alternatively to a sampling based approach. How is it actually being applied? This is a great question. Like, whenever I come across code or GitHub, I try to bring in this table. Everyone else can too, as we build many more. And we'll think of better ways to organize it as the number of examples gets way larger than this. Um, I mean, there's the whole RxInfer RX environments branch that's rapidly growing. There's the and there's a lot of MATLAB and SPM ones that are not added in here, but there's that large branch. Those ones mostly call back to those SPM VBX bays, SPM MDP check. It's like all these kind of names. So there, it's like Friston et al. Curated the functionality of those core utility files, and then papers would use relatively simple generative models and then just know that if it was built a certain way, that the generative and the data fitting directions would work. So that's the kind of MATLAB. There's a long tail of languages like in the Active Inference package, like Rust, Go, Shell, just like a bunch of random languages. They're not super performant, but it's enough to get started. C++, haven't seen any presentations per se using it, but I think some on the more engineering side might be. Of course, one of the major questions is like, well, this is what is known in open source research, but anything other than that, of course, I don't know. On the Python side, there's PyMDP, which is the main Python package. It has a characteristic and lovable slash challenging file structure that can make it a little challenging to get the exact thing you want. However, there's a folder Jax, which is bringing in the kind of Jax, and there's more active work on this in the branches too. So there's a lot of work there, kind of to the chapter 9 theme of fitting from data. There's a lot of other Python work in model stream 14, which was shown briefly earlier. Ran Wei said that Deep Dreamer, he said that Friston said Deep Dreamer, it is basically active inference. So that was, I mean, at least I think Rand said this, which makes sense because one of the collaborators was Danger Hafner. So I think if we kind of just return to the original, what are the applications of ActInf? oh, what methods are people using to apply it? There's the threads and the streams that can be followed from here. And then there's the parallel slash is it ActInf question if you end up with a pragmatic and epistemic element to a RL or meta RL or POMDP type model or something that can be described as such. I mean, has that not reached active inference from the low road by another way? What do you think?
I kind of wanted to ask you about that, especially at the end of the live stream. He was talking about how there's different spaces that you could use, as well as a work that I've never heard of before by Shimon, I think he said, from the Oxford lab. And he was saying that you can think of the model in terms of course, the model itself, where we're doing gradient descent. So we're actually going to be able to talk about gradients flowing in one direction. We can also talk about the actual concept space of the model, like Shimon was talking with representation spaces, I think it was called. And then there's also going to be the thing that we're learning about right now, which is designing the environment through the POMDP, and then having the model learn from that. So there's going to be some environment space, there's going to be some belief space that the model uses to interact with the environment. And then there's also going to be the model itself, which is going to be in the space that backpropagation is really natural. I bring this up because in figure 9.2, like we were looking at earlier, whenever we're actually looking at the model, we're thinking of it in the space of, oh, what are we looking to get out of it? Which may not be the same space. It may be like the POMDP, like the environment space that the model is working with, that we're designing, is not the native space that the model is working in, which is going to be the belief space, which reminds me a lot of Markov blankets, which maybe that has nothing to do with anything. But I thought that was going to be an interesting link, and I wanted to get your thoughts on it. The movement of spaces, the changing of spaces as you move through these squares in figure 9.2.
Yeah, let's return to the question. Let me just copy out what this quote was because I mean this is very interesting that ran well for those who have not seen it. It's really an informative stream. Some of the most information density on epistemic value, pragmatic value, connections with active inference and reinforcement learning. Um, okay, a lot of people's view of Dreamer versus deep active inference. He mentioned that deep active inference has been used in essentially three ways. One of them is when neural networks and other approaches are used. That's also called amortized inference, but that's kind of like deep learning, but deep active inference. The other two are like temporal depth, like long horizon of planning. And then the third is hierarchical depth, like and then we talked about how also those can be flattened. Deep active inference is that many people have implemented is that Dreamer's so similar to active inference, especially I can't remember if which version of Dreamer, and if it does use information gain term in a planning objective, and if it does, then you basically cannot tell whether there's any difference between Dreamer and deep active inference. So in a sense, even Karl Friston has mentioned it sometimes that Dreamer is basically some variations of an active inference agent. What a truth drop. Here was the major approach of the paper, which is the POMDP has an aboutness of uncertainty subjectively. Like the A matrix describes uncertainties associated with the mapping between observations and hidden states. And then the B describes the possibly conditional mapping of states unfolding. Um, that whole picture, though, can be seen as an MDP because, like, if you're programming in PyMDP, you're making a POMDP. But for you, the POMDP is a fully observable MDP. So then there are certain things that you can say that are results that only exist subjectively for MDPs. like chess, but not for POMDPs. But then as a modeler, you can say MDP like things about POMDPs. And it turns out that the key thing that the agent's behavior has to follow along is the information gain. But it really just shows like how different. And then I said something about FEP and the high road and low road. And then he's like, I'm kind of like a low road guy. I don't really have anything to say on that, which was just like amazing and very humble and funny for how informed and how capable his presentation research is. That it's like it wasn't about FEP. He didn't really want to go there, yet he was talking about the free energy functionals with like the highest degree of understanding. So then that's just like, wow, free energy is on the low road. That's the whole thing with energy-based learning, variational autoencoder. I mean, millions of people are using evidence lower bound in model fitting. As Rand pointed out, RL and meta RL and Deep Dreamer go on the low road to indistinguishable from active inference. So that really puts the low and the high road into context. Pretty interesting. Procedural method for I mean this is like live stream 42, but here with three time layers, days, hours, minutes, and then using a procedural method to fill this in, as opposed to like doing this and then that one and then just this and then emitting just from here or something. So I mean, there's so many low road methods. Every method is on the low road, but none of it is in competition with the high road. Like before we started, Zach and I were talking a little bit about the reward learning also, and kind of like, okay, want to build the skyscraper taller. It's just reward function, it's taller. And then in contrast, it's sort of like, I want to reduce my uncertainty about looking from the 100th floor. And then maybe you build a 75 story and jump, or you build a 200 and go to the 100th floor or something like that. But then if there's like an equilibrium that can be reached when that preference is achieved. It's just so interesting to see like how those can yield this, they could yield similar or different computational policies inferred to get there. Like there's situations where um the RL and the ActInf agent would have indistinguishable behavior. And there's situations where they might have different behavior. But at the that would all be situational on literally just specifying, okay, what is the setting? What are the data? Maybe certain generic things could be said like, well, for these kinds of environments, this kind of outperformance would be expected, or this kind of asymmetry would be expected. Some more generic statements about kinds of environments where there'd be different kinds of competitiveness. But I mean, it still is just a basically empirical question.
Do you think biology is going to help us solve that empirical question? Because I remember whenever it was inside of the book that introduced the System 1 and System 2, System Fast and Slow, that's what it was. And oh, I'm sorry. Inside of that, they were talking about the example of, I believe it was falcons that were in California. And so whenever they were discussing it, they asked, what was the value that you would like to apply towards saving this many falcons? And then what they did was either they introduced increasing the space or increasing the number of falcons that you would save, and they asked how much would you be willing to spend in order to donate to this cause? And they started to vary the amount of difference that it would make, and they really showed that like even our own belief systems are unintuitive to us. How we actually value things and how much we value that, especially at different scales, is not something that we would expect from ourselves. Do you think that we would be able to find an empirically good way to solve this strictly from how we function biologically or how any mammal might function inside of us?
Frank or Axel?
Sorry, I just got in here. I've been setting up, so I didn't catch
Oh,
it.
it's all good. Zach, it's a great question, and is slash how is active inference related to being a theory of inquiry along the lines of the pragmatists? What can be empirically and theoretically said about empirical situations like laboratory behaviorism and also theory producing situations considered empirically? I don't know though if even a very strong account there would be equivalent to the resolution of uncertainty or the account for the like the last mile. So you know, as to whether this RL or this ActInf model will do better on explaining this bacteria data set, that's like to know that would be like to know it's like the halting problem. I mean, if you could just it's like it would be equivalent to knowing how a data would fit a model before doing it. You could use heuristics, but and those heuristics may be 100% right in certain settings, but then but that still wouldn't be like actually knowing it. But then you could have certain be like, okay, for linear models or for transformer models, like adding another layer sometimes takes more training time, but it never does worse. Then you could say certain things about two hypothetical architectures being applied to a data set or two models being applied. But it's kind of like the Bayesian model reduction question or like structure learning. You could have a procedure for adding and pruning down latent accounts and all these kinds of things. But like if you already knew which model to apply before, then you might be coincidentally right with your prior, but you wouldn't have been um right except by prior.
Okay, I see what you're saying now. I think I was anthropomorphizing too much because I was thinking of 9.2 and I was thinking that like, oh, the ideal situation would be to where you design a system that's like, oh, it works like I work. So that's where I was coming from.
Interesting. I mean, because it could be like, it works like I think it works, would be like, okay, this is a metronome, and just changing temperature didn't matter. Turning the dial totally explained the frequency of this. So it's like there's situations where this box is, well, or this could be just an AND gate, or this could be just some other discrete or designed system. And then on the other side of the continuum would be like, this is a person talking to another person. And then, but that, so that is that, which one is like, it works like I work? Like seeing the world work as expected, or seeing the world work in a way that is open and surprising. And I think these are become such interesting questions as the technical um as what the our active computational niche is doing around us gets more active, than like what is it that we're really doing. But like OpenAI, of course, ironically, doesn't have, I don't think they released the technical information. It says you can read more of the technical research post. Log linear, but kind of subtle log compute. Better evals on domain expertise. Better coding. It's available in Cursor. O1 Mini doesn't cost any extra. They hide the chains of thought. But it's kind of like, but you don't even know whether what has happened. But it's doing, I mean, so then if it's doing kind of something between working memory, transient chain of thought with pruning, planning and thought, dreaming to plan, planning to dream, maybe using a energy-based method or an elbow, and then like also with kind of a niche modification, maybe chains of thoughts can read and write to each other or something like that. There's just so many architectures people have proposed. Yeah, Axel.
Yeah, I just have a quick question here in the end. I'm sorry I missed pretty much most of this. I was on in transport, but I have a bit of a more technical question. I'm interested in the differences between RL and active inference. And right now I'm going through some of these Pi MDP collab notebooks. And one of the first ones is a tutorial where you're setting up these different matrices for example, like A is your matrix that maps the states to observations. And B is your belief matrix about the beliefs of what will happen if you carry out a certain action, and so on and so forth. And yeah, I think if you open it, maybe the solutions will already be there and you can see what I'm talking about. But in this example, of course, it's a simple one. It's unambiguous. So you start out with all of the matrices that you need to solve the problem, or at least that's how it seems to me. And I'm kind of interested in how little you need to specify. When I first got interested in active inference, I was kind of attracted by the idea that you might not have to specify anything at all. You would have an agent that learns how to carry out useful actions, not by having a reward function, but just by doing things that makes it able to control its environment better, which in the end will be things that uh, perhaps are useful. And I think my question is just how little do you need to specify? Is it possible to specify not even the agent's uh, the agent's understanding of when it sees that it is in square one, it also will think that it should expect itself to be in square one? Like, what is the least thing that I can specify in this setup and still get an agent that learns all of these things itself?
Yeah, great question. Um, First part on RL and ActInf, I think check out this model stream 14 that we discussed a little bit because
Mhm.
it was some of the most distilled and um experienced comparisons. But then this question of like what is needed to be specified. So you're totally right that this is kind of like it's like a canon, inference canon or reverse canon set up on Rails with a certain like it's kind of aimed on a certain axis already because it's like, well, how does it know it's in a T maze? How does it know the semiotics of how the queue at the bottom relates to whether it's on the left or the right? How does it know how to walk? So it's like, but that's where it becomes really important to clarify what are questions about the world, what are questions about generative models, and then where are we developing generative models to address questions about the world? And then those can go back and forth. But it's like, if you wanted to study, well, how does the semiosis become associated between the queue and the T maze? You could study that with a degree of freedom around that relation. Or you could just say, we're assuming it's a perfectly trained rat that already 100% understands like the left and the right cues. But those are generative models that are being constructed for different cases. So depending on what is wanting to be gotten intuition for, like in a toy model, or what kinds of research questions are being addressed from, it's like it'd be like downloading a genome and just like model it. It's like, but I mean, to what end? A 3D shape or like, the regulatory network. It's like, well, all of them. It's like, yeah, but then that's just the whole project of the field or something. That's not a specific research question to ask about. So yes, definitely. And then when it comes down to into this level, is like, yeah. So then, but then what about adding a fourth grid location or how would it come down? Then it has to change it. So those are some of the rate limiting steps in implementing things like structure learning in the models today, which is like the dimensionality has all of these repercussions. Or how would it come to know that it could add a new affordance? So can it be something very simple with a procedural approach to like changing the dimensionality and the number of slices on ABCDE? And then could that, like a procedure over ABCDE, have the ability to learn in this or that way? It's an open question and then, okay, you could set it up, but then if you set it up in a computational environment that only has like multi-arm bandit slot machines, I mean, it's not gonna code in Python. So then that gets into the niche specification, either the computational niche for training and learning and inference, or more of the robotics route with the real world niche.
So, yeah, I get what you're saying in terms of it's interesting how you might want to procedurally change your structure when you've already established it. But then let me ask, what if you have established the exact structure? You live in this simple grid world. You can establish all of that, and perhaps there are certain things you can do in the grid world. Maybe you have to get keys in order to open doors, in order to go somewhere. But there's no final reward in the goal position you want to go to. Do you think an active inference agent, because it's curious and because it wants to learn to understand its world, will figure out how to do the actions which will end up getting it to be able to predict what's gonna or like get the furthest in the world just because it has that incentive, perhaps?
Okay, great question. So what we never really brought a model together, but we explored it, but it was 2021, so it's before like PyMDP and RSinfer and all this, but it was like NetHack.
Hmm.
It's like this text-based explorer
Oh,
that's
cool.
famously convoluted. But even just consider like, yeah, how do you do items as affordances? But then do every turn, are you going to do like this mega deep ActInf on like every possible spell that you could cast in every direction? Or how are we even going to learn to know possibly things that even people haven't written down, like how two spells interact with the dragon only on the 13th level or something? It's like, so this could be a very interesting setting. Again, it's hard in general, but the reinforcement learning or reward approach, let's just say that it's like kind of this surrealist dream grid world with the keys and the doors and all this other stuff. I mean, there's the physiological sort of grounded layer, which, like, what makes more sense, saying I'm rewarded by being at physiology, or I expect to be at physiology and that's just where I satisfy? So let's just say physiology can be equally well explained by ActInf or by a reward term. um then it's like, well, where do you go then with your reward? And then it's like, if you set your reward arbitrary function on curiosity, learning, epistemic value, then you're doing function approximation for epistemic value. So then you've just created a sort of epistemic approximator RL agent. There's nothing wrong with that. It might be totally fine, but it's the low road side of a question that could be approached from a high road, which would just be the epistemic value, expected information gain, things that might be like important for the NetHack challenge. Um, but then how would you come to tune and adjust the epistemic and pragmatic balance on the fly? So it isn't that it, uh, again, thinking about the RL and the ActInf, it's like, let's just say there's a basketball hoop that's 20 feet tall, and someone's like, I prefer myself to be dunking, or the reinforcement learning is just like, I want to reduce, I want to jump higher, and then I'll be able to dunk. But it's like, that doesn't mean it's possible to even do it. But the reinforcement learner would train to jump up to 10 feet, and then they would just stall, and they just would be like, I think I could do better, or I'm at the best score I've ever gotten, or something. The ActInf would just have would reach a plateau of surprise. Like, why am I 3 bits surprised about my jumping when I expect to be doing a 20-foot dunk? But it's like, but if it's an irresolvable situation, then it's been set up that it can't be done. Whereas if it was an achievable situation, then both of those would have a possibility to be able to dunk. But at least leaving the door open for the epistemic and having a stabilized open door that isn't just pragmatic. Because if you operationalize the epistemic value into pragmatic value, okay, we train the reinforcement learning on learning, then we get back to these questions that we were having at the very beginning. Like, well, then it would learn at cost to other variables. Oh no, well then we'll learn to balance that. Okay. But then you can just have this infinite like regress of reinforcement learning, but it still is in pragmatic value from the high road side.
Right. Yeah, I think I'm just having a hard time understanding exactly. There was this paper once about how you could teach agents to learn to ride a bike just by trying to maximize empowerment. So trying to make it so that these agents would uh, not have a reward for having the bike upright, but would have a reward for being able to do more things in the world. And since they had the bike upright, they could drive further and go more places. And because of that, they could do more things. And I'm wondering if the same kind of thing happens in active inference, where if you had an agent in a grid with a place where a key comes out, if it would just go up and see that a key comes every 10 seconds and think that that's nice, and now it's learned that and there's no more surprise, or if it would somehow be incentivized to say, oh, but what happens if I take this key and go down into the bottom of the maze where there's this door, even though it didn't know anything about that would open anything, or
Yeah, Ali was there for this stream with Tom Ringstrom. It's a totally viable path. It's interesting also about the Bellman equations, which come up in the MDP solutions. So treating a POMDP like an MDP, which is say using Bellman optimality PDP MDP style on the agent's POMDP. There might be situations where expected free energy and optimal and empowerment are like correlated, or there might be designable situations where they're differentiable. I think one important note, and it's kind of the separation between the equation 2.5 and 2.6, is like 2.5 variational free energy is not prospective. This is just like a real-time existence check. So this is more like a through the flow of the present. Once you get into planning over expected futures, like there's expected free energy, then there's free energy of the expected future, FEEF. Then there's other approaches that have been proposed. So I think there's a lot of constructions that highlight different parts of the future, to say nothing of the procedural ways that you could like prune through futures. But there might be the heuristic of maximum occupancy, or maximal empowerment, or maximal time discounted reward for some agent, or time discounted learning, or like the amount of this or that within a certain time frame. So I think there's a lot more ways to model the future.
thank you so much. Yeah, I'll definitely check out this paper.
Yeah, it's a great connection though, and I think it's a similar. There might be other intrinsic motivators, like you know, would wanting to learn a space equate to occupying it through a time, equate to empowerment in movement in that space? Again, you could imagine a space where in an agent where like that, those are all indistinguishable. But then they could have some other space where just like, oh, but if the cells change at different rates. So if you are equally occupying the space, then you're not equally learning it. But it's like, but then that's just getting into these more generic like comparators. But I mean, these are great. These are great questions, and um, these are all weaving together in a chapter 9-esque way as we think about generating data from ActInf models, fitting ActInf models to data. I mean, if we can if we can share and borrow infrastructurally with Dreamer and all of these mainstream machine learning models, and contextualize it from a high road and add new paths on the low road, just a few memes away. Okay. Thank you all. see you next time.
Thank you so much.
Thank you,
Yeah.
Daniel. Bye-bye.
Bye.
Bye.